Hello, everyone. My name is Andrei Satarin. I'm going to be talking about this paper, Understanding, Detecting, and Localizing Partial Failures in Large System Software. Rough outline following the paper. We're going to be talking about what even is partial failure, how we can catch partial failures with watchdogs, how the proposed method of generating those watchdogs in the paper is with the tool called OmegaGen. Evaluation of this approach and overall conclusions for the paper. So what even are partial failures? In the paper, they describe partial failures as a failure in the process when a fault does not crash the process, but causes a safety or liveness violation or severe slowness for some functionality. So it's at the process level, not the usual stuff we use in distributed systems at the node level, where some nodes crash, some don't. The process is still alive, so it's not the typical fail-stop failure, again, as the usual ones. The health checks that people implement for those distributed systems could miss those failures, specifically because the process is still alive, but they can still cause catastrophic outages in the real world. So quick recap on the failure hierarchy. The simplest one is a fail-stop. Your process stopped and never restarts again. Something more elaborate is fail recover. Process stops, recovers, and continues with some lost state. A mission failure is where not only that can happen, but you can also lose some packages or request responses. And the biggest of all, the Byzantine failure, process can do whatever. It can even actively have active malicious behavior, try to basically destroy your system from the win. So the way I understood it, they don't mention it in the system itself. The partial failure falls somewhere between Byzantine and the mission failure, because some of them could be seen as a mission of certain packages. For example, your compaction failed, so you cannot do writes. And that means basically all the write packages for write operations are lost, but the system itself is still it can process reads. But some of those failures are even more complex, so they can exhibit somewhat Byzantine failures. So this is why I kind of put them in here. But they don't specifically mention in the paper. This is my understanding of where the area we are talking about. Researchers in this paper basically ask two questions overall. Is like, how do partial failures manifest in modern systems, and how to systematically detect and localize those failures at runtime. So let's dive deep into what they're actually describing. They're researching 5 different distributed systems, well-known, established, mature distributed systems over a wide range of dates. And they found 20 cases for each, 20 partial failure cases for each of those systems, so overall 100 partial failures. And they kind of study what's on those failures, how they exhibit in the system. And they have some of the findings. So first of all of those systems do have partial failures. They exhibit majority of them, roughly 50% in most recent years. So even mature systems do have those. They're not getting ironed out in testing or anywhere else, or just people observe them in production, I guess. Root causes are very diverse, so there's no like a single root cause or majority root cause. 3 top ones is uncaught errors, indefinite blocking, and buggy error handling. Kind of, I guess, usual suspects to a degree.
But finding 2 is flaws in the system. Finding 1 is that these things are happening. Is there anybody doing an analysis of the trend line? Because it feels to me like as data centers get more congested and crowded, it's like freeways getting crowded, and it'll open up and accentuate these failures we're talking about.
I'm not aware of any research in this particular area.
Okay.
Like what the trends are. Is it getting worse or better? I assume because systems get more complex, basically the more stuff you have in a single node, the more chances there are for partial failures.
But also in networks, and network timings, and AZ outages, and AC partial outages, and
yeah. But I guess the way they the partial failures they talk about in the paper are kind of like single noded. So network in that sense, network could be my single node tried to write something over the network and that failed. It doesn't mean the network failed. It kind of like the way they talk about this failure is localized to single node.
Okay.
Network could be like completely healthy, like the way this was.
No, I understand.
Sorry, just a quick question about like the definition of a partial failure. Does this mean it's like it's a failure where the okay, so it doesn't crash, but some functionality is lost?
Yeah, I think they, if I remember correctly, they cite examples like you have compaction or snapshotting and that failed. So now you don't do race, for example. So some functionality is still stuck, but your process is alive because just one of the threads died. It didn't cause the whole process to crash because of a programming mistake or some other reason. It did not, they didn't mean it to be the process level crash, things like that. Or something just slow, you write into disk, but disk is congested, so it takes a long time. So you exhibit slow in a particular functionality, but reads can be still served from in-memory cache, for example, and they would be the same speed as before, or things like that.
So it's definitely, it's very system specific what the partial failure means.
Yeah, or they like basically here the finding 3 is actually, they say like roughly 50% of them are liveness violations. So those are somewhat easy to detect and straightforward. You just see things being slow, means liveness violated, means there's a partial failure. But minority of them are things like 13% are zombie, what they call, with undefined failure semantics, which I also kind of put in the Byzantine failure category. This is why there was overlap before. And some of them are silent, so you have data loss, corruption. So those you cannot detect easily with any kind of simple check. You need to actually understand your guarantees your system provides and deeper semantics. Yes.
Right. Okay. Thank you. Yeah.
70%, finding 6, 70% of those failures are specific to environments. So there's something happening at runtime, so we cannot iron them out with any amount of testing, basically, unless we try to do some kind of elaborate testing. So basically, what authors advocate is like we need a runtime checking because we cannot, we will not be able to iron out all the various runtime scenarios at the testing stage. And majority are sticky, so the process will not recover by itself, but it needs some kind of recovery mechanism or maybe even a simple restart. But other than that, they don't talk about recovery in the paper a lot. They even mentioned this is one of the limitations and something they want to work on, like how to recover from partial failures. At this point, they're only interested in detecting and localizing those. So how do we catch partial failures? And the proposed approach is Watchdogs. So something running at runtime to catch those failures and behaviors.
Andrei, Rohan asked a good question in the chat. Like temporary errors, are they considered as partial failures? The finding 7 suggests that maybe the temporary errors are also partial failures, but 68% of the partial failures are sticky rather than temporary. Is that right, or do we make a distinction?
They mentioned later in the paper in the detection phase where some of them could be very temporary, and we don't want to basically produce a false alarm on that, where something just slow for a second, you just congest the disk, or the other scenario, disk is slow, but it's slow for a prolonged period of time for some other reason, for being congested, or you are out of disk space and that blocks your writes, for example. So I'm not sure, is there like any kind of timeline?
Right.
I don't think there is a definite threshold. So I'm not following the chat though.
Right. No. Okay, good. Thanks.
It's kind of the same with availability and latency. Was it unavailable, system unavailable, or was it just a really long latency?
What's the difference?
Yeah, what's the difference? It's kind of here the same. Like, was it a partial failure, or you just had a slow disk rate? So the current checkers, the current situation, the way authors describe it in the system is checkers, which broadly could be put into different categories. Prop checkers, where you execute something through external API. You have a key value system, you write your keys, you read them back, it works. So your prop checker validates that the system is performing correctly and alive. Or signal checkers, where you monitor some health indicators, basically anything, CPU usage, disk or bytes written, things like that. But they also cite that there are certain problems with those checkers. For prop checkers, the API surface of modern systems is pretty big, so it's kind of hard to cover them with any manual probes. And partial failures might not even be observable at the API level, which I kind of have a little bit misunderstanding with this, like why they saying that. Because if it's not observable at the API level, I am as a customer don't exactly care what happens in your system. Same with the failure get masks, and I'm totally okay with that. So I don't quite understand what they mean here. The signal checkers, they say that they're susceptible to noise and have a pretty poor accuracy, which will be later cited in the evaluation section. So the approach they propose is to have what they call mimic style checkers, basically selected representatives of some operations performed by a main program, where we imitate those operations and detect errors. And because we imitate basically at the kind of lower level operations, we can pinpoint failures with more accuracy to a specific module or even instruction in the code. Those checkers are kind of put in what they call the intrinsic watchdog, which seem to be more deeper integrated in the main program when the usual watchdog, which mostly kind of separate program. So those intrinsic watchdogs have a synchronized state from the main program. So the state of the main programs actually get basically copied into the watchdog. The watchdog executes concurrently, but they still live in the same space, address space as the main program. So they could suffer from the same consequences as like low memory or garbage collection pauses, things like that. So they specifically want them to be there to suffer those consequences. And they advocate to generate those watchdogs automatically based on the code of the program. So this is the example of the watchdog. So the large rectangle is basically the main program, which has different modules, the colored rectangles in the big one, like request listener or snapshot manager. And the watchdog is the thing in the gray area. And it has mimic checkers, where each checker mimics behavior or certain module or thread. And context is basically information copied from the main program to those checkers. So this is kind of like overall how that looks. Basically, we copy some local state to the checkers and execute similar operations. I'll talk more about like how that's done, how we can not ruin the program by doing so. And that in the section about generating watchdogs with OmegaGen. So the OmegaGen is the tool they're talking about, and this is the tool generating all those watchdogs. So overall, there are certain steps you need to take to generate watchdog with OmegaGen, and OmegaGen does that for you. They identify long-running methods. So anything looking like while true, execute bunch of stuff, basically, because this is where what we're interested in. This is where the main method of the program, it's not some startup code, it's what the program is doing constantly over its lifetime. Locate vulnerable operations. Vulnerable operations being something right into disk, right into to socket, but not something like doing computation in memory, like sorting, because sorting, basically any kind of memory operation will not get stuck because of the disk being, or it will not fail in the way they see in the partial failures. After that, they reduce the main program, basically throwing out everything else except those vulnerable operations. And that reduced program getting encapsulated with context factory and hooks, which basically means copy all the local state from the main program to the checker, to the mimic checker, and execute those vulnerable operations in the checker. And then we had checks to catch some faults, and I'm going to talk about this also more. So the same steps example in the code. So the first one is identify a long-running region. This is while running loop. We're taking some snapshots. So this is where we see this long-running region of operations. This is where the OmegaGen will look at. Second step, vulnerable operations. In this case, there is write record. So we're writing something. And the way they describe heuristics for vulnerable operations is basically certain Java APIs like writing to disk or sockets. And here is the vulnerable operations. We're writing some record. Step number 3, we reduce. So basically, there's a serialized node method, and we remove everything from that except local state. We needed to actually call that vulnerable operation. And we insert hooks at the step 4 to copy that local state into the context manager to later get that context and local state in the watchdog. And we generate checkers and add faults and signals. Basically, on the right side, we have the checker, which does basically simple write with the same arguments it copied from the main program. So this is how OmegaGen works, and I'll talk about how it not ruins the program in the process of doing that, generating as watchdog. So after we got those faults, we caught them, we need to validate the impact. Is this actually just a single slow disk operation, or is this some kind of trend? So what they do is there is a certain validation step after each alert internally in the OmegaGen generate set. And a default validation is basically rerun the check. Try to write this again or read this again. Is it still slow, or was it just some intermittent thing? And there are tools to allow developers to manually extend those validations. Next, like one of the parts that OmegaGen has to do is prevent side effects. So because we trying to mimic exactly the same operation with exactly the same parameters, so like I was showing there in the write node scenario, we kind of writing in the same stuff the actual program does. So this is why they do redirect writes. So instead of writing to the same file on the local file system, they write to a different test file, but they still write to the file basically the same data. So if they write megabyte in the main program, they will write a megabyte of data in the watchdog, just in a different file.
Duplicate that write just to test timing, or they will actually put the write there instead of the original place it lives?
They will write to the test file. My understanding is that it will write to a test file, so that there's going to be 2 writes.
Okay, but they're doing that just to kind of sample the behavior.
Yeah,
and they don't modify
it's not every write there.
Yeah,
it is definitely sampled, and so yeah.
And that's to kind of get a sense for what the performance ought to be out of the primary system.
Yeah, they also they have for single operation they have a hard threshold of 4 seconds for timeout. This is their liveness threshold, but they also look at the drift of average time. So if it drifts just slowly, they will detect that too. If there is just degradation of disk or network at like a slower pace, but it's not hitting the threshold for individual operation yet. So all your writes suddenly, instead of 3 milliseconds or 1 second. It will also impact your program, but you will not detect it with a static threshold.
And this is all driven to decide when to kill the primary?
It is all driven to decide where to detect. They don't exactly kill, they just detect that there's a partial fault. You see that writes are slow, and I assume you report it to the operator, because they don't talk about recovery. They don't know, like, is it even safe to kill a program at this stage? Do you want to do that or something? They kind of leave recovery, I guess, to the operator just to report it. With reads, they do idempotent wrappers. So basically, the main program reads the stuff in the buffer, and then checker just reads it from the buffer, just kind of simulate the read, but they also look at the timings and stuff. So for socket operations, they just turn them into pings, so there is no side effects. But another approach they suggest, but I don't think they talk about this in any kind of detailed way, is if you write into another system, so it's not the write to local disk, but you write into different external storage, which is also distributed, you can apply OmegaGen to that system And in theory, your fault detection can talk to the OmegaGen watchers on the other side and kind of decide, did you fail for my use case, or did you completely fail, or what's the state in there, kind of thing. But they just like mention it as one of the approaches for the future, I guess. Evaluation, does this actually work in practice? So for questions, for evaluation stage, they ask several questions like, does this work for large software? Can we actually detect and localize diverse real world partial failures they see in their original research for partial failures? Do those watchdogs provide strong isolation? Do they not mess with the original program? What about the false alarms? Can we are there a lot? Can we lower the threshold, the false alarm rate? What's the runtime overhead in terms of performance and memory and all those things? So for detection, they collected and reproduced 22 failures, so across different systems. And their watchdogs managed to detect 20 out of those 22 partial failures. So they run the systems, injected the faults the way they described in the original bug reports, and the generated watchdogs 20 times out of 22 detected with a median detection time of 5 seconds, which as far as detection time goes, I think that's just an amazing detection time. Overall, they were highly effective against liveness issues. The way they describe it is like, because you don't need to know exact semantics of your program to know it's slow. You just see it's slow, and things like deadlocks or indefinite blocking are there, and you detect a liveness issue. Also effective against safety issues which are explicitly marked in the program, so where there's exceptions or errors or things like that, but they don't say. I assume it's almost not effective against any kind of silent issues, because you need to understand deep semantics of the program to know the data is corrupted.
Andre, question. Did I miss anything? I was away a couple minutes. How are they able to reproduce real world failures? I mean, that's like an impossible task. For a distributed system, that's very, very hard.
I think they mentioned that for every failure, they took them a week to reproduce it. So that sounds like reasonable amount of effort. So basically they run the system, they have 22 real world failures where, oh, if this is slow, the node gets slow and the system like slows down entirely because of the single node or some partial failure. They inject the fault described in the bug report, maybe with some trial and error, with some timing guesses and things like that, or just like trying to, and it will take them a week to, on average, to
so they look at the report. They fiddle with the system to slow stuff down to match the report in real life, and then they rerun it with that slowdown that the thing postulated caused the failure, and then they see this coming, is what they're saying.
Yeah, and they see this from their OmegaGen checkers. Yeah, this is the way I understood it. Yeah.
So the broad idea is you got something out in the wild, hopefully, that kind of knows normal responsiveness. It says, ooh, it's kind of smelling bad. I think I should raise an alarm.
Yes, I'm going to talk about that a little bit later too. So this is detection part. Basically 20 out of 22 got detected, which is pretty good. Localization. In localization part, they mentioned that out of the 11 of those 20 detected, they managed to basically directly point to the instructions, to the instruction that like, if you have a slow write, the watchdog will tell you this write here in code got slow, and it will correspond to the main program because watchdog got generated from the particular point in the main program. For 7 of those, 55% cases, it was either within the same function or the function along the call chain. So it's still better, much better than like just saying, oh, your system is slow, or writes are slow, where writes could be slow for a lot of different reasons because the write pipeline is just a huge amount of work in the system itself, compared to probe and signal detectors where they can tell you, oh, your process is slow, or your large level APIs like writing key values to your key value store is slow. Those basically give you very little localization in terms of where the error is coming from. For false alarms, they also look at the false alarms. And the false alarm ratio they calculate as a total false failure reports divided by the number of total check executions, which I assume if they run, as I mentioned, they run checks every second, means like 86,000 checks a day. And kind of my question here is like, can we trade false alarm ratio, better false alarm ratio for detection time? Because 5 seconds is incredible detection time, median. So basically something gets slow in 5 seconds, you already know it's slow. What if I know in a minute, but the false alarm ratio is order of magnitude better? The actual false alarm ratios are like that. So this is a table from the paper. The first row is Watchdogs. The second row, Watchdogs _V, is Watchdogs validators. So validators is, as I said previously, basically default validator is just rerun the same operation. So if it was slow write, we rerun the write and see if it's still slow. Or I think they mentioned for sometimes they do more kind of manually written validators for some systems, but they don't provide a lot of details on that. So basically, the lowest value here is like 0.01% of false alarms, means 1 in every 10,000, which again, if you run check every second, every day, means you have roughly 8 false alarms a day, which to me sounds like pretty high number in the real world. So it should be either less frequent in terms of how often you run checks, or you need to fight with this false alarm even more. I'm not sure why the other numbers are so high.
And that's the real problem with fail fast, with detecting and killing and replacing in a timely fashion, because as the behavior of the systems gets less prompt with everything, it's not a synchronous network, it's not pulsing, you know, this many times a second, then knowing when it's just sick versus when it's really dead gets harder and harder. And hence there's pressure to not make a rapid decision because of the inaccuracy of a rapid decision.
Yeah. But
you're right. I mean, but you're right. The false alarm ratio should be related to the rapidity of the check.
Yeah. And how comprehensive the validators are, I guess. You can, they don't even mention like, do you do it right, the retry, recheck right away, or do you do like some kind of grace period where you allow the system to recover? Because 2 subsequent writes can definitely be slow if they're separated by a few seconds. Intermittent error, and like a few seconds later, it's all good. Conclusions. So overall, the result of the paper, they studied 100 real-world partial failures in pretty popular software, Zookeeper, Hadoop, and stuff like that. They created the tool OmegaGen to generate those watchdogs from the code. The tool generated watchdogs, automatic or almost totally automatic generate watchdogs, detected 20 of 22 partial failures they tried to reproduce, and they pinpointed scope for almost all of them, 18 cases out of 20, with more precision than just the process being slow. And they also talk in the paper, they actually exposed a new partial failure in Zookeeper. So it's not just the old stuff they were able to reproduce. They found a new bug, which my understanding is was confirmed by the Zookeeper team and was also fixed. So not only old failures reproduced, but new ones also discovered and reported actual partial failure during their experiments. With that, yeah, I'm done.
Thank you.